Assalamu alaikum. Hello.
Assalamualaikum, can you hear me?
Walaikum assalam. Yes, yes.
Okay, perfect.
Okay. So, can you see my screen now?
Yes, I can.
So, we will talk about the exponential function, a very brief lesson for today.
All right,
So,
sounds good.
let's see. It's exponential function, actually a function f of the form where f of x is equal to ax. There is an exponential. Now the variable is coming as an exponent of the constant, and the necessary condition is that a must be greater than 0. This base must
Okay,
be a positive number, and that should not be equal to 1. So only the two restriction is that that should not be 1, because if it is a 1, so 1 having any power, that will become 1, so
the
there is
same
no
thing,
use of
right?
that. So it's called exponential function with base a, and this is the exponent x, and its domain is minus infinity and plus infinity. So it can cover, it can take any value out of these infinity, the two extreme ends. So the next is
Okay,
very simple. So examples. Now the example one is that evaluating exponential functions. Let fx is 3x minus 2. So here find f of 4. So what we'll have to do, actually, wherever the variable is, that is now in the exponents, that is coming as a power x minus 2. So we'll have to replace this x with the 4. And similar, the other example is that you can see this minus 2, but this base is positive 10 and having x exponent, and we are looking for this value. We can find this also. And one more function is that h of x, that is the exponent, that is a fraction and having power x. So once again exponential function due to this exponent, and we can find this. So these are all the different examples of the exponential function. We can evaluate, we can find the values of all these type of the functions. So let's see. We can solve all those what we have seen in the previous slide. That is the F4. So uh, what we are doing, just replacing each and every x wherever the x is. This time it is in the exponents. So we are just replacing the x in everywhere, and we will get the values. Anyhow, let's see rules for exponents. So whenever the exponential functions are given, so we will have to follow the laws of indices.
right.
So basically these powers are called the index. So when the bases are same, then their exponents are added up. So you can say it's a first law. Here you can see that two exponential functions are multiplying with each other. So at this time, bases are same, so just add up their exponents. And this rule is called power of the power rule. When there is the exponential function having the whole power, so powers of the two x and y, these are multiplying with each other. So we can say this is power of the power rule. Similarly, if the two exponents are exponential function or exponent, what we can say, are dividing each other, then there and the bases are same, then there is a difference as a power. And if the exponent is given to the product of two, then it can get the power to each and everything. That is, a is getting power x and b is also getting x. Similarly, if we have a negative exponent, so we can make it as a positive, just changing its position. If it is in the numerator, so it can be in the denominator, just to make it. It's actually the shifting of the function. So we can write just like that, because one having any power, that will remain one. So I'm sure that you are already familiar with all these laws.
Yeah.
Okay. So now it's a very good example that the graphing any exponential function with base a is greater than 1, the exponential growth. So a lot of functions are given, the graphs are given, and you will have to find the, what I mean to say, either their values, their endpoints, the range and the domain, the co-range and other things. Now let's see if the function is given in this format. So here you can see that this is the exponential function with the exponent x, and you are just looking to draw that. The first step is that it's a very helpful if you can make the table for each and every value. What I mean to say, you can start from the middle value, that is the 0, and go for few values on the right of 0, that is x is 1, 2 and 3. And similarly we can go to the left, -1, -2, -3. And if you are putting these values to the given functions, so we can get just like these. So these are actual the different points on the graph.
Right.
Plot the points and draw a smooth curve. So by placing these points we can draw the curve. So let's see, look at this. So this is
Okay.
all about that what we are doing, that the graph is typical for exponential function. So sometimes only the graph is given and you are asked to find out its nature, its equation, its points of contact, the points of turning, its real zeros or anything else, domain, core domain or whatsoever. So from here you can see that first we are locating all those points which we have tabulated in the previous slides. So you can see that previous slides just to recall that. So these are the points 0, 1, 2, 3, and similarly when the x is -1, -2, -3, so the value of the function is becoming just like that. If you are putting x is 0, so you are getting 1, and at x is equal to 1, 3, 9, 27, and similarly it is in the fractional format when we are moving to the left of 0. So anyhow, so now we are plotting these points. So look at these. So these are all those values which we were putting in the real function for x. So when x is 0 and 1 and 2 and 3, and similarly when x was -1, -2 and -3. So all these values of the x, if we are just joining these points in a line,
Right.
so we will get this curve that is representing y is equal to 3 raised to power x. So I'm sure that it's self-explanatory, no need to explain this.
Yeah.
Okay, so today I'm in a bit hurry, so we will go very fast. Anyhow,
Yep. That
uh,
sounds good to me.
you can ask anything. You can interrupt me. But anyhow, these are simple things, so that's why I'm going. Okay, now let's see. Graphing an exponential function with a lies between 0 and 1. So look at this, sketch the graph of this function. It's a fraction because a lies between 1 and 0, it cannot be equal to 1. But anyhow, it's a half and whole raised power x.
Right.
So solution is first that we will have to make the table. So it's a general rule that you must start from the middle, putting the x is 0 and then go at least 3 values to the right and 3 values to the left of 0. These are the negatives. So you can put the values, you will get these points. So we will have to locate all these values on the graph, and that is on the next slide. So from here you can see, look at this, the a lies between 1 and 0, that's a half. And as x increases in the positive direction, y decreases towards 0. So here you can
Okay.
see that was the y is equal to half of the exponent x. So If you are putting zeros, you are getting this. And if you are moving to the right of 0, that is the positive values over here. So this graph is coming down. And if you are putting the negative values of x, so -1, it's rising up. For the minus x is equal to 2, it's further rising. And this trend will continue if you are just putting the negative value of this x. So this will go up and up. So this is the general shape or the format of the equation. Anyhow, we are just going to properties of exponential functions. So properties mean let f is a function, that is the exponential function. A is always greater than 0, that and also this must not be the equal to 1. So the domain of fx is, if you are asked to find the domain of any exponential function, so state weights minus infinity and plus infinity, and they can ask about the domain. So if you can see all those sketches, or if you can log on to Delta Math, so they are asking, they are putting, they have the boxes that what should be the domain, and you will have to click the right domain, either minus infinity or plus infinity and both the ends. So from this for that the every exponential function has the domain minus infinity to plus infinity. The range or the codomain of this function is 0 to infinity. 0 to infinity, because it's an exponential function, it's a positive a, and that should not be equal to 1. So this will always go to the right. Look at this. So it's a touching the line, but it will never cross the line, and this will go up and up. So that's why it's starting from 0 to infinity. So range is just like that, 0 to infinity. That may go to 0 when y it's touching the line over here coinciding the x-axis, and this will go to infinity up to the y-axis. So this will go up and up to the infinity. The entire graph lies above the x-axis. So you can see, can you see this, that how can you visualize this, that this entire graph is
I could see the graph.
above the x-axis. So the graph rises to the right, and f is an increasing function. So sometimes I have seen a lot of examples that in the delta math side, so there were the functions and they are asking about their trends. Either these are increasing function or decreasing. So from here, if you can make the guess that it's a exponential function, then you must say that it is increasing to the right. And as x is increasing to infinity, y is also increasing. As x tends to minus infinity, so if you are just putting the negative values, so y becoming 0. As you can see, at -1, at 0 it is coming down, and -1 further coming down, -2, and at 3 almost touching the y-axis. So I'm sure that everything is clear. So we should move to the next slide. So once again, one more function is given in this way, that the exponential, this if f this decay is actually the function, it's an exponential function. We'll talk about that in the next slides also. F is a decreasing function, so that the graph falls to the right. So look at this. As x tends to infinity, y tends to infinity. So sometime the graph is going up from the left side. So if you are coming down to the negative values, so this will increase going up. And if you are taking the positive values, so this will become over here. The graph of fx ax has no x-intercept. It will remain above the x-axis. So it has never crossed the x-axis. No value of x will cause fx to equal to 0. The graph is a smooth and continuous curve, and it is minus 1, 1 over a, 0, 1, and 1. These are the few points. The x-axis is a horizontal asymptote for every exponential function of the form fx is equal to ax. So here we are using the asymptote. Asymptote is the line which is just touching the curve but never crosses it. So this time we have the x-axis, and if we are just trying this curve that is a given exponential function, so it will never cross this line, that is a y-axis. So that's why it is the asymptote to the x-axis, but it is not the asymptote to y-axis. As you can see, it is crossing the y-axis at this point, but this will
Yeah.
never cross the x-axis. So asymptote is, we will talk about the asymptotes when we'll talk about parabola, but this is a new word for you, asymptote. So asymptote is a line that go along a curve but never cross that curve is called the asymptote of that curve. Sometimes the parabola, hyperbola, ellipse, circles are given, and we're asked to find the asymptotes. So we will have to locate those lines. But anyhow, I'm sure that you're clear about this word asymptote, that the line which goes along the curve but never crosses the line, the curve is called asymptote. Anyhow,
Yep.
we are moving to the next. So transformation of exponential function. So here you can see that fx is equal to ax, exponential. Transformation, the horizontal shift is y is equal to ax plus b, and effect on equation is shift the graph of y is equal to x b units, that is left of b if it is greater and right of b if it is less. So if you are just adding the, what we can say, one more constant to the exponents. So horizontal, vertical shift is that ax, and you are adding a constant to the function. So here we are adding in the exponent in the powers, but here we are adding at the end of the exponential function. So this will be vertical shift. So we are just moving it up, and horizontal shift, we are just moving it to the right or left accordingly. If it's a positive, then it will be on the left, and right if it is negative. So shift the graph of y is equal to x b units up if b is greater than 0. So vertical, so it will be above the 0. And if b is negative, if you are getting a negative number over here, so you will have to move the graph down to the 0 up to how many units? B units.
Okay.
So the other transformation is that if a constant is multiplying, so you can see that transformation of the exponential equation function is f of x, that's a raised to the power x, the exponent is x now, transformation equation and effect on the equation. So transform is stretching or compressing vertically. So if you are multiplying with a constant c, multiplying the y coordinates by c, the graph of y is equal to a raised to the power x is vertically stretched. If c is greater than 0, it will be stretched to the above, and compressed, it will come down if c lies between 0 and 1. But it's not a negative, but it is coming closer to the 0 and less
Okay.
than 1. If it is greater, it will expand. So other transformation is that reflection. Reflection mean that this is a positive function, and if you are just getting a negative sign just to making it a reverse direction. So reflect the graph of y is in the x-axis, and if you are taking raised to the power minus x, reflect the graph of y ax in the y-axis. So it's a totally reflection. What I mean to say, if reflection is just like that, that you are multiplying with minus 1, so this will be reflected on the y-axis, and if you are making the exponent 0, oh sorry, negative, then it will be reflected on the y-axis. Anyhow,
Okay.
we will see some graphs also.
Okay.
Sketching the graph. Now let's see, use transformation to sketch the graph of each of the functions. Now here you can see that is b, and here you can see one more is added to the exponent, and here you can see the function is multiplied with negative number, and the last case is that multiplied but there is another value, that is the positive b. So here the
Right.
negative b. State the domain and range of each of the function and the horizontal asymptotes of the graph. So this time we are looking for the asymptote also. So
Okay.
this, look at this, that if you are considering the a part only, the first example, f of x and 3 raised to power x minus 4. So its domain is minus infinity and plus infinity because it can go to every direction on both the sides. There is an arrow, it can go. So this is y is equal to 3x, and here y is equal to 3x minus 4. So it's coming down because it's a negative. So range is minus 4 and infinity. It's coming down now. Horizontal asymptote y is equal to minus 4. Now you can see that y is equal to minus 4 if you are just coming down to this point, and if you can draw a straight line, asymptote is a straight line. So this will go
Right.
along the curve in this way, but will never touches or crosses the curve. So this will be a straight line over here running through the negative 4 on the y-axis. So the next is b. Here we have f of x is equal to 3 raised to power x plus 1. So actually, when you are taking x plus 1, so this is the actual blue color is representing the actual graph. Now it's transforming in the way that x plus 1. So x was here, and you are just moving it to up direction, that is x plus 1. So y will become 3x plus 1. So this is the curve moving to the going upward. Domain is as usually minus infinity plus infinity. Range is 0 and x. Infinity, what we can say, horizontal asymptote y is equal to 0. So every y, so y is this one. So when y is 0, so this will be over here, and you can draw the line, straight line through this point, and this will never touch this line. So replacing x in 3x with x plus 1, shift the graph 1 unit left. So we have shifted this one. Similarly, if you are considering the next example with a negative x leading coefficient, or what we can say, the base is now negative.
Right.
So domain is as usually, every exponential function has this domain, and range is this one, horizontal asymptote is this. Originally, actually, this was f is equal to 3 raised to power the x, and you are now just making the reflection. Reflection is actually the mirror image. If you can put the mirror in front of that, so you will get this type of the graph. So it's a now, this was for the upside, and this is now downward. This is due to this negative sign, and this will go in this way and this way. So the next is this one. When you are adding uh, one more constant unit to the 2, so this is the original. Here you have this negative, and you are just
Okay.
putting 2 units away, so it will go up. So that's why all these graphs are given. So the
Okay.
general exponential growth decay model. So A amount after T time. So these are basically for the radioactive elements in chemistry. Original amount is this one, and rate of decay, that is R is less than 0. Growth is R greater than 0. And this I
What?
is the exponent, the number of times periods. So half lifetime and quarter lifetime. So anyhow, this is just the type of the exponential function. Compound interest, here we are using also the exponential function, as you know. We'll talk about that in detail. But compound interest is the interest paid on both the principal and the acquired previously earned interest. It is an application of exponential growth, exponential function. Interest that is compounded annually is paid once on a year for the, this is the actual amount and principal amount, the original amount, 1 plus the rate at which it is growing up, and time, the time period of the investment. So
Okay.
another example is that this amount is deposited in the bank at the rate of this compounded, and we will have to use that to solve. But this is not our problem. We are just talking about the applications of the exponential function. So here you can
Okay.
put all those values, you can get the answer. But compound interest can be calculated in this way. So using different compounding periods, so annually, semi-annually, quarterly, but this is not our topic, but these exponential functions are being used to calculate the compounded interest. So this is just like that, monthly. uh, One more thing is that bacterial growth. Sometimes these type of the questions are given in the SAT exam. That a technician to the French microbiologist Louis Pasteur noticed that a certain culture of bacteria and milk doubles every hour if the bacteria amount Bt is modeled by the equation. So this equation is given with T and R's, find the initial number of bacteria, the number of bacteria after 10 hours, it is doubling now. The time when the numbers of bacteria will be 32,000. So we are using this equation, and this equation is actually due to this exponent is becoming the exponential function, and this is the rate of the bacteria. So we can solve just like that. Initial size is when the time is 0. So B0, B, and this is the initial amount. And when you are putting time period is 0, so this will become 1. So anything power 0 is 1. So this was the initial amount of that. Next, after 10, so you can put the 10 for the time period and you will get this amount. Find t when this will be this one. So here 2 raised power t, you are looking for t. So after solving that, you will have to make the basis same just to get the exponent same. So in this way, 16 can be written as 2 raised power 4. When the bases are same, their exponents are also equal. So that is 4. After 4 hours, that is the quantity. So these are all the applications. So value of E,
Okay.
that is the uh, as H gets larger and larger. So Euler number E, that this was the mathematician who first time discovered its value. And similarly, continuous compound formula. So we can put this exponential function, and I think this is all about that. This is find the amount when the principal amount. So we are not going to solve that, and how much money. So this is all about that, the question and the solutions. So the natural value of this function, this is also the exponential function. E is, you can say, the natural value of E. So one more example, we can draw the graph of this Euler constant exponential function in this way. So I think that this is all about the what I mean to say, the graphs and the exponential function. So model for exponential growth, that is, we have talked about that. So this is all about that. So this is the end from my side. So I am looking for the new topics. So this was the last of the series about the functions, and I'm sure that if you can recall all those things, so you will be in a better position to answer all those questions which are given in the graphical format. You can find out the end
Right.
behavior, you can find out the domain, the codomain, you can find out the turning points, you can calculate the absolute zeros, you can sketch the maximum and minimum values, you can talk about the increasing and decreasing functions, you can talk about the stationary point. So these were all about those what can say topics we have covered during these series of the lessons about the functions. But anyhow, if you are feeling any difficulty, so you can ask, you can send that particular problem, or you can ask about that we are, if we are missing something about the functions, so you can ask at any time. Just text me, just send a
Okay.
message, just send the screenshot of any particular problem, so I will that solve, and will be with a great with the all explanations of all the steps. So anyhow, so I'm looking for some new topics, because we have talked about a lot of discussion was about the functions. So I think we are
Right.
getting bored about these functions topics. So a lot of lessons
Yeah.
we have covered. So just for the taste change of taste, so we must talk about something else. Okay,
Yep. Sounds
are you
good
getting
to
me?
me.
Are you getting me?
Yeah.
So definitely,
Yep.
if you are studying online or whatsoever, so there are so many other topics other than the functions. Am I right?
Right. Yep.
So
You're right.
we should talk about something else. So that's why I'm that this time I'm totally blank that what's going on over there in your regular study. If there is some other topic, so we should touch that and we should study in it in
Yeah.
detail. So
Before our spring break started, we got
yes,
into logs.
okay, logarithm. So you
Yeah.
will have to send some
Yeah, I could do
because
that for you.
logarithm is a very what we can say a comprehensive topic. So I just want to see the level of difficulty that and that level is very much clear if you are sending some problems, some screenshots. So I will get that level and I will make the all those lesson according to that level, because if logarithm I am just preparing the slides or going through the lessons, so that may be under level or over the level of that of your difficulty. So that's why I'm looking for the sample or example problems and all those outlines or contents in any shape. So I will come to know that this is our level of study, and we will definitely talk about the logarithm, the laws of logarithm, and their evaluation, their algebraic notations, their whatsoever, a lot of things are there about the logarithm. Okay, so I will wait
Yep.
for that. So this is all about from my side. So anything you want to say or you want to ask or you want to share, so you're most welcome.
I don't have any questions right now
Okay, so
or anything of that sort right now.
so
So
once
I
again
think we're
as a
good.
reminder, so you must send these screenshots of the next topic.
Yep.
Okay, thank you very much.
All right, we'll do.
Allah
Yep.
Hafiz.
All right. Office.
Allah Hafiz.